So is that all working?
Yeah,
Great.
go for
Okay,
it.
cool. So thanks everyone. Pretty excited to be here today with you guys. So I will be talking about a Surface Code implementation for Qiskit that was originally built over the summer as part of one of the Qiskit Summer Gems. And so we'll talk a little bit about what happened there and then some of the progress that we've made since then. And yeah, so I'm Henry. I'm an undergrad at Yale. I do currently some research on bosonic error correcting codes. And so we're not, neither of us are experts at surface codes, but we thought it'd be an interesting way to just get familiar with how everything works. And also, I think exploring it through Qiskit is a really good way to just get I think an in-depth hands-on sense of how things are working under the hood. I also want to thank the other members of our team for the hackathon, Shada, Will, and Andy, who unfortunately can't be here today to present, but they were pivotal in kind of establishing the original project. Cool. Okay.
Yeah, and maybe I can also give a brief introduction. Yeah, so hi, my name is Shantanu. I'm a senior in the math and physics major at Yale. My current research is more experimental, so this was a fun project into a bit of theory. But yeah, I work on trying to establish universal control over this weakly coupled superconducting cavity and transmon and ancillary transmon system with applications towards bosonic quantum error correction codes such as the GKP code. So this is pretty fun working on this quantum error correction protocol that may not be realized in experiment until maybe not in a few years, but it's fascinating and beautiful theory. And I guess a motivation for us when developing this was to make it something like the repetition code, which is not only a good quantum error correction protocol, but also a good tool to learn. And so that's what's gone into a lot of this project, making visualization tools and making it really something that someone can get up and running on their own device and learn more about what a surface code actually is and run some useful benchmarking. I guess I'll hand it back to you, Henry.
Cool. Thanks, John. So just a quick overview. I will be introducing the surface code concept and theory, and then also talking about the encoder that we've developed. And then Sean will take over for the decoding part and some of the benchmarking. So feel free, by the way, if there's any questions, I guess you can interrupt and ask, especially if anything's unclear. So just to start off, I wanted to talk and give a brief review of quantum error correction, just to motivate the problem. So I think most of us are probably familiar with the repetition code tutorial that IBM James Wooten has written and championed. And also, I think many of you have seen his quantum Qiskit Global Summer School presentation, where he goes into some of these details as well. So I'm not going to repeat the details there. Kind of pick up where that leaves off. If anyone is interested, I definitely recommend checking those out if you haven't already. And then I also want to mention another resource, which is Steve Girvin's Yale Quantum Institute series on classical quantum and quantum error correction. And some of these slides are kind of borrowed from lecture 3. So just as a very brief review, reminder for everyone, in the classical case, we're kind of concerned about what kind of classical bit errors might happen if we try to store information. And I'm going to talk about storing qubits and bits first, but at the end, you can kind of generalize this also to operations. So in the classical case, you really have, you're isolated to kind of discrete bits. Classical bit can only be 0 and 1. And so there's two kinds of errors that you're mostly concerned with. The first is a bit flip, so going from 0 to 1 or 1 to 0. And there's also maybe a less common, but also a possibility of having an erasure. So in kind of similarity to the quantum case, it's sort of like a decay of bits, but we model this as basically going from 0 to 0 or 1 to 0. On the quantum case, it's a little bit different, because certainly now you first have a whole Pauli group of bit and phase flips. So you can experience an X error, a Z error, or a Y error, which is just a composition of the X and Z errors. However, you can also experience kind of a more general, not a discrete set of errors, but rather coherent rotations of your qubit around the Bloch sphere. So basically, this is an arbitrary parameterization of any combination of X, Y, and Z errors. There's also a few sets of non-unitary errors in terms of damping and erasure, but for this tutorial, I kind of won't cover those in depth. The other interesting thing about quantum error correction is that we have to take into account the issue of quantum back action. So in comparison, of course, to the classical case, we need to make measurements, diagnose, and correct these errors on the quantum bits without actually knowing the particular state in which the error occurred. And so this is actually a significant requirement that kind of influences all of the decisions that go into this. So I'm going to talk a little bit about the repetition code from a slightly different perspective that I think has been covered before in the tutorial and in the lecture. And this introduces a little bit of the stabilizer formalism that I think if you start to look at some of the papers on surface codes and QEC type and the family of codes in QEC, you'll kind of encounter this a lot, so it's worth going over. So as a quick reminder, we can set up a 3-qubit repetition code. So we encode a logical 0 as a set of 3 physical zeros, and similarly a 1 is a repetition of 3 physical 1s. So of course, we're working with quantum states. So an arbitrary logical state has arbitrary amplitudes alpha and beta. And so in general, the logical state of a qubit is some superposition of these two. And so you can notice, let's say we have an X error on the first physical qubit. So this is we're just modeling a single qubit flip. And that takes us into the states shown on the right-hand side here.
Right, and it does look like you have a question in the chat box as well.
Yes. Sorry, I am actually not sure how to get to the chat box.
Don't worry, it's just Amir is asking if you could share a bit more about what you mean by coherent.
Oh, I see. So, sure. So in this case, what I mean here is that the amplitude of the qubit is being preserved. So this is a rotation around the Bloch sphere, but there's no, we're kind of still in a unitary case. So in general, in an actual quantum computer, you can have non-unitary errors because your qubit is coupled to the outside world. So you can have cases, for example, like I think like amplitude dephasing is the most common one, where basically you have any state and it just decays to the ground state. So that's a non-unitary. That's an example of a non-unitary error. In this case, I just wanted to kind of restrict the error model to the coherent unitary case. Okay. So going back. Oh yeah.
Oh, I was just going to say, it sounds like you answered Amir's question. He says thanks.
Okay, perfect. Yeah, sorry, I can't actually see the chat, so it's a little tricky. Okay, cool. So going back to the repetition code, so we have the situation that we've presented on the left. So the problem is, in comparison to the classical case, is that we can't actually diagnose this error by measuring the individual physical qubits. And you can kind of see this like saying, if I actually measure the qubit and I'm in some sort of arbitrary superposition of 0, 0, 0, and 1, 1, 1, or in this case, by measuring it, I collapse it basically to one of these instances. And so obviously, if we, that lets us diagnose the error, but we can't do any useful computation from this going forward. So instead, what we want to do is measure something called the code stabilizers. So this is kind of like an indirect way of identifying flips, but without revealing information about the state in particular. So we can define 2 code stabilizers and basically say the S1 stabilizer is actually a measurement of Z1 and Z2, and the S2 stabilizer is a measurement of Z2 and Z3. And so note that this is not actually the same as measuring Z1 and Z2 and then multiplying the results. Because if we do that, we're actually in that case that we described before, where we collapse the state. But what this does, you can kind of think about this. I don't want to rehash the details, but if people have questions about this, just let me know. So for example, if I apply S1 to the 0, 0, 0 state, that means I want to measure Z1 and Z2. But as we know, if we apply a Z gate to 0, that returns a phase of 1, essentially. So nothing happens. And then if we do the same thing on the second qubit, it's the same thing. So 1 times 1 is 1, and we get an unchanged state. So the thing to notice, though, is that the stabilizers, if performed on the opposite logical qubit of all ones, this actually gives us the same thing, because a Z on the first qubit returns -1, Z on the second qubit returns -1, -1 times -1 is also +1, and we are still in, and so we still get the same state back. The difference, though, between doing this and measuring them individually is that we don't actually know the state here. All we know is that these bits are the parity of these bits are the same, but from this information alone, we don't actually know which one of these states we're in, and that's essentially the crucial piece of information that lets us do correction successfully. Okay. Hopefully, there's no questions, and I'll move on to. Okay, so you can kind of take this stabilizer formalism and kind of construct this little table of the 4 different correctable error states, 1 qubit correctable error states of our 3-bit quantum repetition code. I'm not going to go into this in detail, and you can kind of maybe match this to what you saw on the previous slide. But basically, if I have a qubit flip on either the first qubit, second qubit, or the third qubit, I can distinguish these by using the values of the stabilizer that I have received. However, I don't actually know, for example, if I'm trying to get to a logical 0 or a logical 1 state. So these 2 classical bits of information that I receive from the system don't collapse my logical qubit, but it still allows me to correct errors successfully. So the question that I think we want to ask now is, of course, in this case, notice that there's no way for us to detect a Z flip. And this is sort of just by design, by the nature of being in all of these qubits are in the Z eigenstates already. So the question we want to ask is there actually some sort of state that is an eigenstate of both Z and X? And it turns out that there is, and these states are the Bell states. So you can kind of quickly see this by going through this diagram. So if you do a Z flip, or sorry, if you measure Z and Z of this Bell state, you basically get the same thing. And it's the same thing if you do the X and X states. And so I am going to jump into the notebook real quick that we prepared, and I think it's informative to look at this maybe from a like, I'm not going to prove it, but we can kind of watch how this behavior actually evolves. So in the notebook, I basically just set up same thing, and I'm going to set up a circuit that basically prepares a Bell state and then does 2 rounds of repeated ZZ and XX measurements. And so I think if people are confused or interested in the details, definitely refer back. All these notebooks are on GitHub. But basically for now, you can basically look at it and see. So this is the Z1, Z2 measurement. Sorry, it's a ZZ measurement, an XX measurement, and then we do it again just to verify that we are actually in an eigenstate. So I've set up a little test circuit that just verifies, that basically constructs the 4 different Bell states, 4 different possible Bell states, and then runs them through the circuit. And this is just a schematic of the final one. So we prepare the Bell state here. This is just a standard implementation for preparing, for example, the XX Bell state, and then we run it through the circuit. And when we look at the readout measurements, we see that these numbers, these stabilizer syndrome results correspond to the table that's given here. Obviously, the exception being that the notation is flipped from +1, -1 to 1 and 0. But in some sense, this is kind of like the proof is a little involved, but you can kind of show that actually the fact that the stabilizers these are stabilizer eigenstates actually do completely describe the underlying state of the system. Cool. So the The other important thing to note is that if we look at a given stabilizer eigenstate here, we actually don't know if we are in if we prepare a ground state of the system. So rather than looking at a Bell state, if we look at, for example, the GG or GG plus EE state or the GG minus EE state, this is actually a superposition of these two stabilizer states. So we can kind of look at this as a basis transformation. We can either describe the system in the basis of the underlying qubit states, or we can simultaneously say, given a single ground state, for example, we can also describe it as a superposition of stabilizer states. And this is a kind of a useful formalism. And if we run the state again on just not a Bell state, but rather just a 0, 0 qubit state, we can see that half the time we're projected into one of the stabilizer basis states, and the other half the time we're projected into another stabilizer basis states. And this essentially matches up with what we are expecting. So I definitely recommend, I think some of this stuff is hard to wrap your head around just listening to it. So I definitely recommend kind of playing around with things and seeing how they change. And that's a helpful way to get a sense of things.
Yeah, I guess one thing that really helped me when I was trying to understand this, so the 0, 0 is itself a superposition of this plus state, which is, or not really plus state, but the Bell state, which has a plus, so GG plus EE and GG minus EE. So if you add those two together, you can see that that's, well, 0, 0. And so if you start off in 0, 0, you're starting off in a superposition of the eigenstates of your stabilizers. And so if you measure with your stabilizers, you're going to project into one of these eigenstates. And so that's exactly what Henry was talking about. When you start off in 0, 0, you're either going to end up in GG plus EE or GG minus EE. And you can see that from the stabilizer measurements that you get. So you either get plus 1 plus 1 or plus 1 minus 1. Mm-hmm. Or in this case, we're using zeros and ones. But and once you're in that eigenstate, so from that first syndrome measurement, once you're in the eigenstate, you stay in the eigenstate. So if you're in 1, 1 or 0, 0, sorry, in this case 0, 0, then you stay in 0, 0. And if you're in 0, 1, you stay in 0, 1.
Yeah, those are really important. I think that's sort of like the crucial part of what this is demonstrating. Cool. Okay. So now, given these, given sort of like this stabilizer formalism, we can kind of ask, how does this solve the continuous error problem? Like, as I mentioned before, we don't actually only have, only X and Z flips, but we actually have X, Y, and Z. So luckily, Y is a combination of X and Z, so that's easy. But we also have this continuous error, continuous coherent, arbitrary phase evolution that we have. So the crucial, and I kind of like this pithy summation of formulation of things, is Korotkov's law, is in quantum mechanics, you don't see what you get, you actually get what you see. So what this means is that actually, if you measure no error, there is no error, and that if you measure an error, you actually collapse the state directly onto the stabilizer eigenstate. So even if you are in a slight rotation of errors, once you measure the stabilizers, it actually will project you into either into one of the possible superposition eigenstates that you get. So obviously, if you're slightly rotated, that means that you might have like an uneven chance. You might only have a small chance of being in the far eigenstate and a large chance of being in the close eigenstate. But once that measurement and projection is made, you actually no longer are in kind of like this continuous realm, but even though the qubit is kind of subject to continuous errors, you're actually correcting discrete ones. And so this essentially enables the whole endeavor of quantum error correction and ultimately fault tolerant quantum computation. So we can go ahead and start extending we can take the repetition code, what we've learned in the repetition code, and we can take the stabilizer formalism and put them together to make the toric code, which is basically the precursor to the surface code. And I recommend there's a series of posts by James on the Decodoku blog that kind of introduced the intuition, and they were super helpful for me. But basically what we want here is with repetition code, we can only determine X flips, but with this sort of Bell state stabilizer eigenstates, we can measure both x and z, which, as I mentioned before, gets us y and any continuous code. At the same time, we also we want to preserve basically a large distance between logical code states. So if there are small probability of errors on any given one of the qubits, we want the sort of the number of errors that are needed to take us from one logical code state to another logical state to be large. And then the other crucial part of the code, the property of the code that we want to ensure, is that when we measure any given parts, any individual part of the code, it only reveals a small portion of the state. So that's sort of like the property that we mentioned before, where we don't want to know too much information. And so if we use stabilizer eigenstates as logical states, we can kind of start to construct this toric code, where basically we say, okay, let's tile a bunch of physical qubits in sort of a lattice pattern. And this lattice is actually going to be living on a torus. You can kind of imagine the top edge connects to the bottom edge, and the right edge connects to the left edge, and that makes first makes a cylinder, and then it makes the whole torus. Then we say that the only valid logical states in our system are ones in which we have kind of complete loops of flips. So we might not have all 0 physical qubits. We might have 0 physical qubits, and then these 4 have become 1. But this is still a valid state as long as they form a loop. So you can kind of imagine any loop on the torus is fine. But what's not fine is things that don't form a complete loop. So how do we actually use this to encode a 0 or a 1? So we can kind of start to say, okay, let's assume that this is a 0. But there's an interesting property which we can look at, which we can say and we can define that a logical 1 state is any state in which there are a complete ring of 1 qubits that have been flipped around the entire donut. So both C and D both satisfy these properties. So C, you can kind of imagine this red line is this red line, and as long as that's true, we know that A, this is still a logical state, a valid logical state, because it forms a complete ring. But B, now that if we traverse the circuit in the vertical direction, that if we look at the parity of all these qubits, then we get an odd number, and the odd number is what encodes the logical 1. And so similarly, you can look at, so these are still valid states. If we count the parity along this line, obviously you have 1 plus 1 gives us a 0, so that's still a 0. So that fits. This is still a logical 0, as is A. And then similarly here is the same thing. We can actually we don't have to look at this line, we can look at any of these lines. And as long as we have a complete loop around this, around the donut, and you can have multiple, as long as they're odd, multiple number of odd loops around the donut, this encodes the logical 1. So I know this is a little bit quick. If there's any questions on the intuition here. And I definitely recommend looking through the blog posts because they have a wealth of information. Okay, so as I mentioned before, by enforcing this kind of loop property, we can essentially get a sense of what's not a valid logical state and use that for error correction, which Sean will kind of cover in depth later on. So for example, here are 2 examples of situations where we have we're outside of the logical code space because there's no loop. So if we only have 1 qubit flipped here, that means there's no loop. Same thing here. We have 3 flips, but we haven't completed the chain. So neither of these states are within logical state. And given this information, we can use that to correct, to basically correct us back into a logical state, and hopefully that takes us to the one that we're hoping to get. All right. So in reality, basically service code is just the torus, and obviously we can't build a quantum computer that's shaped like a donut. We have to cut it at the top and the bottom, and just make it a flat surface. And so the difference here is that these edges no longer connect to these edges, and the same thing with the vertical edges. But it's been shown that this is essentially equivalent property-wise to the donut. And then so this is the sort of the default service code. The one that we implement in Qiskit is actually a rotated service code. So we just take this entire lattice, we rotate it by 45 degrees. And what this does is it actually creates a little bit of symmetry between the Z and the X states. It also reduces the total number of qubits that we need. And so this is the one that we will implement. And there's more details you can look at, kind of like how this is actually working. Recommend looking at this paper below. So now that we have kind of the overall geometry, the qubits in the service code, we also need to basically make the that I talked about before. And so this is a slight extension from the ZZ. In the stabilizer code, obviously we have 4 qubits surrounding each ancilla. And so what we'll end up doing is we'll make a ZZZZ and an XXXX measurement. And this is totally fine though. If you kind of work through the algebra of the details, it still preserves the same properties and it still has the commutative properties that we're expecting. And the way that we do this, again, these details are kind of gone into in depth in the paper. They're not super important now, but basically we just we entangle in sequence, in a certain sequence, BADC to do the X stabilizer measurement. And then similarly, we do, in this case, BDAC. And these are just slight optimizations. The ordering is important, but again, you don't need to worry about sort of why it's one way or the other in this particular case. Cool. So that's kind of like an abstract representation of how everything is working. How do we actually implement it in Qiskit? So I'm going to demo the circuit that we built. And basically, the general procedure is we initialize all of the data qubits. So these represent the data qubits. We initialize all of our data qubits, and we run a round of measurement. That round of measurement projects us into basically what's called a quiescent state of the system. And so that's one of the eigenstates of the superposition. And that's the state that in the absence of errors will be preserved until the end of time, essentially. And so the way that we do that, but in the presence of errors, we actually have to measure, we can use the syndromes to measure whether or not there's been errors. And the way that we do that is we do the process that I mentioned before. We entangle all of the data qubits with the stabilizer qubits, and then we simultaneously measure all the Z's and all the X's. That's the readout information that we're going to use to code, and then we reset, and that's a single round. I'm not going to cover that for now. Basically, it's about degrees of freedom. I think if there's any questions about that, we can talk about it. So that's a sort of schematic diagram of the connections. If we incorporate the ordering that I mentioned before, it kind of shows up in this pattern. So for the X0, we'll end up entangling these in order, and then for the Z's, we'll entangle these, and these go in order. So in the notebook, I have the same diagram here. And basically this Qiskit, manual Qiskit code here basically just runs all of the entanglement chains in order so we start with the top left, so we entangle these and this one, and then we go here, and then we do all of that. We can place that stabilization into the actual circuit, and then we can draw the resulting circuit. Fairly complicated, but it's not too bad once you kind of take a look at it. Basically, at the beginning, everything's in a 0 state. The first round, as I mentioned before, will project us into a quiescent state. So we take all of these. These are the sort of, you can see like in the first case, there are 2 entanglements and then 4, and then these will basically entangle each of those sections in order. And then in this part, we basically do all the measurements simultaneously. And then each round will basically add an entire one of these blocks. So that's sort of like a manual case that I think it's helpful if you want to look at how it's actually being done. In our library, of course, we have generalized this and created this class called surface code logical qubit. And you can pass in a distance for the code, and then kind of have these convenient measure functions, methods really on the qubit that run the stabilization rounds. So the result of this generated circuit should be the same essentially as the manual one we created. Now, we can start actually kind of going through and measuring what's happening in the circuit. So if we start off in the logical 0 state, because of the quiescent state measurement and the superposition, we actually the first round will project us into one of 16 possible eigenstates. And so I won't go into like too many of the details here. You can kind of read through this in the tutorial, but this property is essentially what hides the total logical state of the qubit from us and makes it so that we can run error correction efficiently without actually destroying the superposition of the useful information that we're actually trying to encode. And then, yeah, so in the interest of time, I'm going to kind of skip through this very quickly. You can define similarly logical operations like a logical Z operator, and then start doing the actual readout of the qubits. And I'd recommend, if you guys are interested, definitely take a look through the tutorial because it explains it in depth. But basically here, what I do is I run through 4 different examples of a logical 0 state, logical 1 state, a plus state, and a minus state, and just show that if you look at sort of the syndrome measurements in the absence of noise, they are stable across rounds. You get one of the 16 possible states, that stabilizer states to be in, and then the first kind of line encodes the actual logical value. So
just to tie it back to that first part, where we were talking about GG being the superposition of the eigenstates of the stabilizers. Yeah, if you, I guess, scroll up to that first set of, yeah, right there. So yeah, we see that if we start out our data qubits all in 0, then that's already an eigenstate of the ZZZ stabilizers. That's why if you look at the first 4 digits, and it's kind of you have to orient yourself as to how to read these strings. So the syndrome measurements happen are listed in order from last to first. So the first stabilizer measurement is actually like this last string, and we see that the 4 of those measurements that correspond to the 4 Z stabilizers are all 0. Because 0, 0, 0 is already an eigenstate stabilizers. However, just like Henry was saying, there are 4 possible values for the 4 X stabilizing plaquettes, and we can be projected into any of these eigenstates. So just like before, how GG was a superposition of the eigenstates of our stabilizers. In this case, having the data qubits be in 0, that's also a superposition of 16 different eigenstates of our stabilizers that we can be projected into. And once you're projected into that, you stay in there unless there's noise. But yeah, yeah,
it's a really helpful clarification. I wish if I had more time, I would kind of go into these in detail, but I think the tutorial lays it out, and you can kind of explore some of this. And then just to finally, you can kind of, just for fun, we can kind of visualize, distance 5 surface code, which is a lot larger, but in sort of like actual use in the future, if surface codes become sort of the way that we do fault-tolerant computation, the distance will be much larger, maybe like 11, 20, 30. They have to be odd, but sort of like on that order or even larger. And then I would recommend playing around with this, and I think this gives like a very strong intuition for what's going on. So the service code library that we have, you can kind of construct a state, we can run a stabilization, and then we can basically manually insert noise into the system and see how it affects the eigenstates. So so in this case, it's a noiseless simulation, but I'm basically saying I'm going to choose to have qubit 6 and qubit 9 be flipped, and you can kind of see, you can match this up with the way that the syndrome readouts are structured, and see within the actual syndrome measurements how that identifies the actual qubits that end up being flipped. So in this case, if we flip qubit 6 and qubit 9, which is qubit 6 is here, and qubit 9 is here. If you parse this readout, you can kind of see that you actually get syndrome flips at 0 to Z0, Z2, Z4, and Z5. So this qubit being flipped will flip these 2 syndromes, and then this qubit being flipped will flip Z2 and Z5. But I recommend definitely playing around with this and kind of getting a deeper sense. You can kind of like hands-on play with this. Cool. The final thing, so yeah, definitely recommend everyone, like, it's a work in progress. We're definitely open to suggestions on, whether or not this is a kind of sort of useful abstraction to go forward within. The main question I think that we're kind of considering and looking forward is the fact that the service code logical qubit is obviously on the logical level, it's a qubit, but at the physical level, it's kind of this entire circuit. So if you kind of think about going one level up the abstraction ladder, right now you construct physical qubits and put that into a physical circuit. But maybe in the future, we'll have kind of design an API that looks something like you're putting logical qubits within a logical circuit. And then this is actually composed, instead of being, this won't be 2 qubits, this will actually be, was it 19 each, I believe. And so sort of all of these, it kind of hides away all of this complexity underneath. And then if you call, for example, an X on the first logical qubit, logical surface qubit, this will kind of proxy the call into sort of performing the logical X on the underlying qubit. But this is kind of something that we're hoping to maybe get, if people are interested, in discussing further, is sort of like what the best way of going forward with this representation is.
Henry, I've got an idea about that.
Yeah, absolutely.
It would be fun to see what would happen if we plug this in as like a transpiler pass. So I don't know if the transpiler allows you to extend the number of qubits, but it would be interesting to take just to treat it as a pass, and then the same way that we kind of just because then you could rely on all the work that's been done there, just in terms of infrastructure around this. Although it would be a little bit confusing in terms of you would need to know whether you're operating at this logical level or physical level, for other passes. But just a thought.
Yeah, absolutely. I think that's a really interesting direction to go. I think I saw recently, it's not exactly on the transpiler side, but I saw recently, I think in one of the recent releases of Qiskit, we're starting to introduce ancilla qubits. And so I wonder if we can add maybe it makes sense to kind of start adding in some idea of a logical qubit that can kind of be during the transpiler pass, be optimized, compiled into the underlying representation here. So yeah, but if folks are interested, definitely after the talk, love to chat more. Cool. Okay. So if there's no questions, I can't see the chat, so I don't know if there's questions in the chat, but if not.
Nope, nothing in the chat.
Okay, cool.
If not, you mind if I ask a question?
Absolutely.
I'm super curious about this being implemented on a real device and how far off it is, what's the, how far can we get, all that kind of stuff.
Absolutely. That's really, really good question. So obviously, I think the main hurdle that you can kind of see right now is that, so this is a distance 3 qubits, and you need 8 data qubits, 9 data qubits and 8 syndrome qubits. So for basically a single logical qubit on distance 3 is sort of the minimum distance, but in practical use cases, it will be a lot larger. So for every logical qubit, it takes 17 physical qubits. So even if you consider the large 70 qubit machines, that kind of superconducting qubit machines that exist today, we're still in a scenario where this kind of goes in the direction of fault tolerance. So there's definitely a lot of hardware development that will be needed to make this kind of a reality. But at the same time, something like this, if not surface codes, but some sort of fault tolerant error correction code will be necessary to kind of get to that final holy grail of fault tolerant quantum computation. So I think you can maybe benchmark a single logical qubit on some of the IBM machines. The other tricky part right now is connectivity. So I think, as I understand, the trend right now, because of some hardware issues, is to kind of go for less connectivity. So, for example, each of these syndromes needs 4 adjacent qubits, and that may not be possible to kind of actually arrange this on a real device at the moment. So it's definitely more of an educational and kind of future-looking thing that we can't necessarily do physically right now, but in the future, hopefully it can be realized.
Cool. Thanks.
If you don't mind, I'll piggyback on that question. So does the surface code, does it require a physical layout? So obviously, if you implemented this, there would be a lot of swaps with our current hardware. And I'm just wondering if it's, if it's contingent on a physical layout that matches this this layout, or
Sure.
if it actually still works even with swaps.
Sure. So I think in theory it could work with swaps. The downside, of course, is that every swap you add kind of introduces even much higher error rates. So I think as a first pass, my guess is that like a working service code implementation will probably most easily be implemented on a square lattice, an actual square lattice layout machine. But perhaps in the future, we'll find some smart ways to try to transpile this thing onto arbitrary layouts. But basically, every additional swap that you add just introduces, I think even right now I think it's one of the worst gates in terms of error rate, right? So it's just tricky there. Cool. Okay. Yeah. So with that, I will pass it to Sean for the decoding part.
Sure. Thanks, Henry. I'm going to share my screen now. So please let me know if you can see everything. Yeah, does it look good, I guess? Okay, cool. Yeah, so I'm going to pick off where Henry left off. And yeah, so there's this idea of under noise, our stabilizers will give us useful information. We call these syndrome measurements about the errors that have possibly occurred in our surface code. And so the next portion of this talk will be talking about minimum weight perfect matching decoding, and specifically the example of a logical readout using a logical Z and correcting that logical readout given what we know about our syndrome measurements. Yeah, so to reiterate, I'm going to give an overview of syndromes and error chains. And so this is our surface. Can you see my mouse, by the way? Yeah, okay.
Yeah, we can.
Cool, thank you. Yes, so we have this, we're using this rotated surface code layout where we have these plaquettes where the red plaquette is measures the ZZ in the case of this semicircle, or the ZZZZ syndrome. And essentially you can think of it as a bit of a parity measurement on the lattice vertices that surround it. So yeah, so each of these lattice vertices is our data qubit. And we see we have 25 of them in the case of d equals 5. The center of each of these plaquettes, there are 24 in this case, and so you can just kind of count these up. 12 of them correspond to these ZZZ stabilizer measurements, and 12 of them correspond to these XXX, or these X stabilizer measurements. And so as an example, let's see what happens when we have an error on our data qubit, so the lattice vertices. So let's say we have a Y flip, which means an X and a Z error. Well, in that case, so in that case, it's important to note that the Z stabilizer plaquettes, so these red plaquettes, they measure X flips in their nearby vertices, while the X stabilizer plaquettes, they measure the Z flips. So if there's an X and Z flip error in this data qubit, then this X syndrome node will go off, and since there's also an X flip over here, this Z syndrome node will go off to show that there is an X flip over here. And we can actually simplify how we create this correspondence between our syndromes and the errors that have actually occurred. Because in simulation, what we're going to actually have are these yellow circles, or these syndrome measurements, and what we want to is what's the most probable error set, or set of errors that have occurred on. And so let's say these syndromes go off over here. Then we know that, or let's say there is an X on these two data qubits. Then, and by go off, we mean it'll change from the previous round. So before, let's say it had some parity. Now, since only one of these corners has changed, the parity will change. And so we'll detect a change in this syndrome. Over here, since two of the corners changed, the parity will not change. So this syndrome node will not change or go off. Over here, since only one of the corners flipped, there will be a parity change, and so this syndrome will go off. And so in the end, this error chain will lead to these syndrome measurements. There is, however, something called a logical error. So imagine you have an X flip on all of these 5 data qubits. Well, in the same way that these were the syndromes that corresponded to this error chain, the syndromes that will correspond to this error chain will actually be these floating circles. And these floating circles are what we call virtual syndrome nodes. So these are ancilla qubits that we don't actually have in our system, and so we don't have access to these measurements. So if such an error were to occur, we wouldn't see any change in our syndrome measurements. In fact, Henry touched upon this briefly before, but this is related to a degree of freedom that we have that allows us to actually store quantum information. So if you notice, we have 24 stabilizers and we have 25 data qubits, and so there's this 1 degree of freedom that we can use to actually store quantum information. But the summary is, if you have a column of X flips, or really any path that goes from this edge to this edge, then you incur what's called a logical error, which means errors on the data qubits that won't result in changes in our syndrome measurements. And thus we can't detect them, and so we can't correct them. So to dive deep into how we actually solve this problem of starting off with some syndrome measurements and coming up with the most probable error set, we go to something called the syndrome graph. And so what I've displayed here is the Z syndrome graph. And just to emphasize this point again, the red corresponds to Z stabilizers. However, they detect X flips, which can be a bit confusing, but that's why we've labeled them with an X in the sense that they detect the X flips. However, this is this graph, which connects real and virtual syndrome nodes, is called the Z syndrome graph because it's made up of Z stabilizers. And again, it's sensitive to these X flips, and we can kind of go through an example. So let's say these data qubits incurred an X flip. Well, what might happen? Well, then we would get these syndrome measurements as we talked about before. And how can we use the syndrome graph to figure out the most probable error chain, or rather to figure out that these qubits were the ones that actually went through an X flip error? Well, we can connect, we can create a perfect matching between the syndrome nodes that went off in a way that's also minimal weight. And so that just means that on this graph, we want to connect these syndrome nodes in a way such that the connections have the least amount of total weight. And why is that? And why does that correspond to the most probable error set? Well, we can actually call the we can quantify the probability of an error set, and where I call an error set is defined to be basically matchings between syndromes. So not even the specific flips, but just matchings between them. So for example, matching these two syndrome nodes and these two syndrome nodes is one error set, whereas matching these two syndrome nodes and matching these two syndrome nodes is another error set. The probability of this error set, it corresponds to, if you go through some math, it corresponds to, well, the probability of, this probability is proportional to the negative of the summation of the edges that are involved in defining this error set. And so in this case, we see the summation is 3. And since there's a negative sign here, we want to minimize the number of edges that we use in our error set. Yes, and a nice way to think about this as some intuition is that the most probable error set is the one that involves the least amount of data qubit flips. And so, yeah, for example, matching these two would correspond to 2 data qubit flips, whereas matching these two would correspond to 1 data qubit flip. And you know, the careful viewer might note that, you know, this is not the only possible chain. You could also have a chain that goes through here, which would correspond to a flip over here and a flip over here. But the thing is, we could actually correct for this chain, even if this is where the data flips occurred, because of the way in which we do our logical readout. So a logical readout, a logical Z readout in this code corresponds to a parity measurement across these data qubits. And so let's say we encoded a 0, an X flip would change that logical readout to a 1. So this error would change the logical readout that we actually get in simulation to a 1. And then through minimum weight perfect matching, we would say, okay, there's an error chain between these two syndrome nodes, and regardless of how we realize that error chain, like in this way or this way, we're going to find out that there was in fact an X flip on this row, and so we would correct that 1 that we got back to a 0. Also, feel free to interrupt me at any time. Just like I also can't see the chat right now for some reason. I think maybe when you're sharing screen, you can't. But please feel free to turn on your mic and just like start talking with a question. Yes. So okay. So how do we actually do this in practice? How do we do this? How do we solve this problem of going from syndrome nodes to the most likely error chain? So we start off, and this kind of brings me to our to one of the 3 notebooks that we've prepared that are good tutorials that go through our package of encoder and decoder, and also a benchmarker that I'll talk about later. But yeah, so if you look at the Z syndrome graph, which is basically this purple graph, we can see that in our code it looks strikingly similar because it's the same thing as this diagram over here. And another cool way to understand these edges of the syndrome graph is to look at the 1s, which correspond to the actual data qubits. So you see how this is a 5 by 5, and so you have 25 data qubits, and depending on which of these edges we connect, correspond to detecting errors on particular data qubit values. So we start off with this syndrome graph, and then we focus in on the syndromes that we've actually detected. So let's say we detected these syndromes in yellow. You can see that there's a one-to-one correspondence, but you also have these virtual syndrome nodes. And the idea there is, okay, we know that the real syndrome nodes went off, but we don't know whether the virtual syndrome nodes went off or didn't go off. And so we kind of have to include them in our analysis. Then we take this error graph, we call this an error graph, and just to kind of zoom in on this error graph for a second, the edges that connect these vertices, these syndrome nodes that we're interested in, so the real syndrome nodes that have gone off and the virtual syndromes, the edges correspond to the minimum paths, the minimum weight of paths between these vertices. So for example, let's say going between this real syndrome, which corresponds to this vertex over here, and this virtual syndrome. You can see that the minimum path has a weight of 3, and so just for the purposes of our algorithm, we add a negative sign, but it's -3 over here, the edge that's connecting them. And then we take this graph and we actually look at the nearest neighbor connections. And we get this sort of matching graph on which we can actually do a minimum weight perfect matching. And now what we essentially take are, we include the syndrome nodes that have gone off, as well as the virtual syndrome nodes that are closest in the sense of this distance to our real syndrome nodes. And on this, we do our minimum weight perfect matching. And from this, we find that there's an error chain between these two syndrome nodes, and there's an error chain between these two syndrome nodes, which corresponds to what we might expect. And from the actual structure of the syndrome graph, we can figure out where, or give options as to where these flips may have occurred. Yeah, so we start off with a syndrome graph. We go to this error graph, we go to this matching graph, and using minimum weight perfect, and then using the Bossum algorithm, which I'll talk about briefly, we get this minimum weight perfect matching, which corresponds to the most probable error chain between our syndromes. And so what exactly is minimum weight perfect matching? Well, just to make it explicit, a matching of a graph is an independent, edge set of edges without common vertices. So you can see here that this is a matching because these edges don't share any vertices. A perfect matching is a matching that matches all the vertices of the graph. And so we do a perfect matching on this, except I'm only displaying matchings that include real syndromes. But this perfect matching, the reason why it's a perfect matching is because our virtual syndromes are connected to each other and not displayed. But yeah, so a perfect matching is a matching that matches all the vertices of the graph. So we do a perfect matching on this matching graph. And then a minimum weight perfect matching is the perfect matching that has the minimal weight, a minimal edge weight, which we saw before corresponds to the most likely error set. And so this is a well-known combinatorial problem that can be solved using something called the Bossum algorithm, which is what we use. There's an added optimization. Also, yeah, so you feel free to, and I encourage you all to go through this tutorial, which actually goes to this, this exact problem and breaks it down. And at the end, we're also able to use this architecture to figure out that, which qubits have actually flipped. So this says that there's been an X flip to 3 qubit, which is here, and an X flip on the 3-3 data qubit, which is here, and then a Y. So in this case, I also included a Z flip. So that's why it corresponds, like an X flip and a Z flip will give you a Y flip at this data qubit over here. Yeah, so please go through this tutorial to cover some of the topics that we can just give a brief overview of. But there's an added optimization that we incorporated called a minimum weight perfect matching with degeneracy, and the idea there is that if that certain error sets have a higher degeneracy in terms of the paths through data qubits that can realize them. So over here, I show one error set in gray that has a degeneracy of 1, because you can have a data if you connect these two syndromes, and if you connect these two syndromes and you connect this syndrome to a virtual syndrome, the number of paths through data qubits that could realize that, there's only 1. However, if you look at the matching between the matching in purple, the error set in purple, if you connect these two syndromes, there are two possible paths that you could take through data qubits that would realize this error chain. And there are 2 over here and there are 4 over here, so this gives us a degeneracy of 16. And the idea is the error sets that have a higher degeneracy will be more probable. And so you can kind of go through this math and you find that the probability of an error set has this positive term, so there are 2 minus signs here, but this positive term which increases with the degeneracy, with increased degeneracy. And so if there are more ways to realize an error set, then that error set is perhaps more probable. And so an important distinction between these 2 error sets is that this gray has only 5 qubit flips while this purple has 6. And so you would expect that the error set in gray would be more likely because it has fewer qubit flips. However, in simulation, we can see that if we don't include degeneracy, then we do get the matching that corresponds to weight of 5. So there's 1 flip here and 2 flips here, 2 flips here. And if we do include a degeneracy rating, let's say p equals 0.1, and there is a certain p is the probability of an x flip actually occurring on a data qubit, and p has to satisfy this sort of inequality for this specific case to be true. But for p of 0.1, we see that the most probable error set has 6 qubit flips. This is an interesting optimization. And actually, we do generalize this. So right now, I've been talking about t equals 1, which is just 1 round of stabilizer measurements, but we can generalize this to multiple rounds of stabilizer measurements. So you keep stabilizing your surface code, and you keep getting syndrome measurements. And the idea there is your syndrome graph goes from something that's 2D into something that's 3D. And we've written some pretty useful visualization tools, and this is in line with the kind of purpose of this package as being something that can help people learn about surface codes even before they're implemented on hardware. And the idea here is before the edges of our syndrome graph corresponded to data qubit flips. Now the vertical edges correspond to ancilla qubit flips, so measurement errors. So since these syndromes are XORed with each other, if you have some syndrome XORed in time, so if you have this syndrome go off and then it changes in the next round, then you can then one possibility is that there is an error in the ancilla qubit that you use to actually measure these syndromes and these stabilizers. Yeah, so the general flow is you start off with a readout string, kind of in line with the repetition code convention. You start off with a string which has a logical readout, let's say a logical readout of Z, and syndrome measurements. So for D equals 9, this is actually the case of D equals 3 and T equals 3. You have 8 syndrome measurements, and you have 3 of these XORed syndrome measurements. And yeah, so using this information, these syndrome measurements, you can post-correct this logical readout. And the general flow is you start off with a syndrome graph, and this example is detailed in this notebook. You start off with the syndrome graph. You do the same kind of things that you did with the 2D case, but yeah, you go from syndrome graph to error graph to matching graph to the actual minimum weight perfect matching. And the end result is that you get a set of most probable flips on our data qubits, which you can use to post-correct your logical readout. And so maybe to talk about benchmarking briefly. So we want to actually test the performance of our surface code with a varying physical noise model. And so what we do is we have this benchmarking tool, this convenient benchmarking tool, and we have this thing called the logical error rate, which is essentially given some logical readout, how often are you able to post correct it to the correct logically encoded value. And so we can get a graph of the logical error rate versus the physical error rate. And of course, we have to define an error model. And so our error model in this case is an X flip or a Z flip or identity. So it's a depolarizing error channel that includes just X's and Z's. We didn't include Y's right now, but later we can. And the idea of how we insert these errors is we have the first round of stabilizing measurements. For the case of t equals 1, we have you have this first stabilizing measurement that projects you into that eigenstate of the stabilizers. And then you can have errors happen on these identity matrices. So if you look at our error model, we only have errors occur on identity matrices or identity operators. And then you have another round of stabilizing measurements. And so, of course, this isn't maybe the most comprehensive noise model, but it's a good start that kind of demonstrates the power of the surface code, which is to correct errors between syndrome measurements. Yes, so this is the circuit that we're working with to create a graph like this. We change the physical error rate, so a P error that goes into this error gate over here, we sweep that, and we get a corresponding logical error rate. Basically, how often are we able to post correct the logical readout correctly? Or and so what we see is there's this break-even dashed line, which is essentially is it worth using a surface code, or is it better to just encode a qubit into just one physical qubit, one physical qubit? And so this is kind of the dashed line. And for the d equals 3 case, we see that yes, it is worth it, at least for these physical errors. And then we can also vary t, so we can perform rounds of measurement. So rounds of stabilizing, and we see that this logical error rate does go up. However, if you look at the logical error rate per round, then it's around the same within statistical uncertainty. And so, yeah, the idea is that this logical error rate per round kind of stays kind of the same. There's still a bit of an increase as you increase physical error rate. And then if you vary D and just look at one round of measurements, we actually got a result that we were not expecting from theory. And you do see like some behavior that you might expect. So with a larger surface code, your logical error rate increases. But there's this concept of a threshold. So the idea is there is some physical error rate below which larger surface codes can give you, larger surface codes can give you a lower logical error rate. And so you can below this threshold over here, you can increase the size of your surface code until you get an arbitrarily low logical error rate. Above threshold, you see that larger surface codes are actually worse. And so you can't reach an arbitrarily low error rate because you can't go below 3. We don't see that sort of intersection here, and this we think can be because of a few things. We think maybe the noise model we're using isn't completely correct. Maybe we're not using enough shots, and another thing might just be there might be a bug somewhere inside here. But in terms of errors that we could think of, at least, and we did do extensive testing, our decoder works pretty well. So this is definitely an improvement to see this sort of result that we would expect, that we would love to get some input on from people who go through this repo. And that brings me to the outlook of this project. And so to summarize, what we were able to do is we were able to encode a logical qubit in a rotated surface code using Qiskit, and we made this wonderful package in which we're able to abstract away these stabilizing measurements, these these stabilizing measurements, these readout measurements, and logical operations, and even setting the logical state. And we also made a minimum weight perfect matching decoder, which is able to detect depolarizing errors in post-correct logical readout pretty well. The outlook of this project is that we want to create this logical circuit that Henry was talking about, with further abstraction, where we're able to incorporate not just single qubit gates, not just poly gates, but also non-Clifford gates, and also a 2-qubit CNOT gate using some lattice surgery, which essentially takes these lattices and glues them together in clever ways. We want to improve the decoder to account for unequal X, Y, and Z error probabilities, so more general error channels. And we want to conduct more extensive benchmarking by varying the size of the surface code and the number of stabilizing measurements, exploring these various types of noise models, and hopefully see that threshold point. And the end goal is to incorporate this package into Qiskit Ignis and have it be a tool that people can use, just like the repetition code, to learn more about quantum error correction. And maybe in a few years, implement it on actual hardware. So yeah, so this is our hackathon team. Henry and I are here, but we also had 3 amazing members who contributed to all aspects of this project. And so yeah, so thank you so much for listening to this talk about our project, and also thanks to James Wooten for creating the repetition code and these tutorials and actually talking with us. And we had a nice call with James about what we needed to do to make this something that could be incorporated into Qiskit. And thank you also to Doug for some perspective as to how we might want to implement this on hardware and why we might not be able to at the moment. And of course, thanks so much to the Qiskit community. And that's our talk. Thanks so much.
All right, thank you. That's great. Does anybody have any last questions before we wrap up?
Yeah, I have a question for you, either of you. There's a lot I didn't understand, but the part about the minimum weight perfect matching, is that something that you anticipate would be implemented alongside a lattice as like by a classical computer that's running that, or would you actually insert weight states into, would you have a separate like quantum mini quantum computer running an algorithm? I quickly looked up
really
Blossom.
Cool,
yeah, because I was thinking like as this scales, I mean maybe it's tractable with only a 5x5, but I'm just wondering like
yeah.
You have to have real-time results, I assume.
So there are 2 things here. The first thing is that this is a post-correction.
Oh, it's post-correction. Okay.
Yeah. So I mean that might change a bit. Though I think that this will remain a post-correction. So, but then that's a important note. So the Blossom algorithm, there've actually been some optimizations that implement this, like using multiprocessing, and it is a combinatorial problem. So I guess maybe someday, hopefully, you can using a quantum computer. But yeah, it is a post correction.
Okay. Yeah, that was well, that clarifies that. I wasn't sure if it was required at runtime to occur. Okay, thank you.
Just to add, I think very quickly, the reason it's post correction versus kind of in while the circuit is running is because in a physical system, doing the correction may itself cause additional errors. So, if you can kind of prevent that from happening, then it's ideal.
See, yeah.
Awesome. All right. Well, thank you both so much. It was a great presentation, and I'm gonna excuse me. I'm gonna end the recording, and then this will be available soon for everybody to watch, and we'll post that in the channel.
Yeah. Thank you
Thanks
so much,
again, everyone, for attending. Yeah.